Hello class, welcome to this video on Chapter 6 review, Part 3. So we're looking at Lesson 6.3. So let's go ahead and get started and dive in. By the way, you're going to want to make some, a correction on the numbering of the problems, because we have 38, 39, 40, 41, 42, 43, and then that one goes back to 42. So you want to change that from 42 to 44, and then obviously you're going to change the rest of them, 45, 46, so on and so forth. Okay. All right, so we'll go ahead and dive in because we have a lot to cover here. So 6.3. So each of the 12 classroom teachers at an elementary school, 2 from each grade level, kindergarten through 5th grade, randomly selects one student from their class and asks them about their bedtime. Let X be the number of students who have a bedtime later than 8 p.m. Which of the following provides the best reason why X is not a binomial random variable? All right, so looking at A, it says there are more than 2 possible outcomes since the number of possible bedtimes is infinite. All right, so that's not true because in this case, what we're looking at is we're looking at whether they have a bedtime later than 8 or not, right? So it is binary, so it satisfies bins. Remember, for binomial variables, it has to satisfy bins, right? So binary mean either success or failure. In this case, bedtime later than 8 or no, bedtime not later than 8. So it's not going to be A because that's not a reason for why it's not binomial, because here it does satisfy the B in bins. B, the teachers don't choose students independently of one another. Well, it does say that they randomly select one student from their class, right? So they are um, so that wouldn't be a reason why it's not a binomial random variable. Okay, so we can eliminate that because again, they're selecting the students randomly and all that. The number of students being chosen is not fixed. So is it fixed here or not? It says each of the 12 classroom teachers, 2 from each grade level. So they do have a fixed number of people, right? So that wouldn't be a reason why it's not binomial. Okay, so that's not right. Okay. And then we'll look at D. The probability of choosing a student with a bedtime later than 8 likely differs by grade level. That actually is a good point because if you look at it, there's 2 from each grade level, kindergarten through fifth grade. And so if you choose kindergarten students, they're more likely to have a bedtime earlier than 8. And then as they get later on in the grade levels, 5th grade and so on, they're more likely to have a bedtime later than 8 p.m. So this is a good point that the probability of success is not the same by student. So, and remember that the S stands for same probability. The probability has to be the same across the board, but it's not. So therefore, yeah, I would select D for the answer. All right, so let's look at the next one. So on number 30, it says when people apply for their driver's license at the Department of Motor Vehicles, their eye color is recorded. In the U.S., the proportion of people who have blue eyes is 0.7. What is the probability that at least one of the 5 people who apply for a driver's license on a particular day has blue eyes? We want to assume that the 5 people are not related in any way, and they go to the DMV independently of one another. All right, so let's see. Does it satisfy bins, right? Let's see if it satisfies bins. Is it binary? Well, yeah, either they have blue eyes or not, right? Are the people independent? Yes, we can assume because it says here that they go independently of one another, and they're not related. And the number of trials the same? Do we have a specific number of trials here in this example? Well, yeah, it says 5 people, right? So that's our number of trials. So yes. And then the probability of success, is it the same? Well, yeah, it's 0.27 for blue eyes for every person. All right, so it's a binomial random variable, so we can use the binomial formula. And it says we want at least one of the 5. Okay, so the probability that X is greater than or equal to 1. Okay. All right, so the probability of success we said is 0.27. the number of trials is 5. Our X value is greater than or equal to 1, right? But I'm just going to put 1 there. And then and I think that's it. So that's all we need. So now we can go ahead and we're going to do the binomial CDF function. We want to do the CDF function, guys, because it's an inequality, greater than or equal to. But remember that the CDF function can only do less than or equal to, right? It can only be used for less than or equal to. For x is less than or equal to a number. And so what we need to do is we need to manipulate this to get less than or equal to. Okay? So we are going to, before we use the binomial CDF, let's manipulate this. So remember that if I want greater than or equal to 1, if I want to convert it to less than or equal to, well, the opposite of greater than or equal to 1 is less than 1. So what we're going to do is we're going to do the 1 minus the opposite, okay, which is less than 1. Now, less than 1 is still not less than or equal to. But what we could do is we could just say that this is less than or equal to 0, right? Less than or equal to 0. Or we can, well, if it's less than or equal to 0, that means it's 0 because you can't be less than 0. So therefore, we could just say it's 1 minus the probability that x is equal to 0. And in that case, we wouldn't need the CDF function. We would just use the PDF function, because PDF function is when x is equal to a number, right? And here we have x is equal to 0. So we might as well use the PDF function. All right, so we have 1 minus binom PDF trials equals the number of trials is 5. The probability of success is 0.27, and then our x value is 0. Okay, for this particular scenario. Okay, don't get this confused here. This value of 1, it comes from that. Okay, but here we're using 0 for this particular thing. Okay. All right, so here we go. So we got so if we do this on the calculator, again, we're going to show you how to do that. All right, so here's a graphing calculator. By the way, guys, I didn't mention this earlier, but you can actually have access to this calculator online if you type in ti84calc.com/ti84calc, and then you'll get a free version of this. I mean, it's just on the web. So, and you'll be able to just do this on the web. They do have ads around it. But you know, the ads don't cover the calculator, so you can just use it. I mean, the ads are annoying, but I mean, if it's free. So just so you're aware. So here we go. So we got 1 minus binom PDF. So that's what we're going to do. So we're going to type in 1 minus, oops, not list 1, 1 minus, and then we're going to go second vars. And we're going to go down to binom PDF. I'm going to go all the way down to the list. So I'm just going to do the up arrow. That'll take me down to the bottom of the list. And then binom PDF. We have 5 trials. And we have probability of success is 0.27, we mentioned. The x value is 0. All right, and we get 0.793 almost, right? 0.793-ish. Right, and if you look at the multiple choice, it looks like about 0.7927, right? So the answer is A. All right, so there you go. So that's a binomial type problem. So let's look at 31. It says University A, 19% of undergraduate students have declared a major in business, while 7% of undergraduate students at University B have declared a major in business. A random sample of 250 students at University A and an independent random sample of 250 students at University B were selected. Assume students declare their major independently of one another. Okay, so, all right, so the independently. If the two samples are combined, what are the expected total number of students who have declared business as a major and the standard deviation of the total number of students who have declared business as a major, respectively? Okay, so first off, So we have two different variables. We have 19%, then we have 250 students for that. So we're going to call that P1, I guess if you want, 0.19. We have X1, or no, I'm sorry, N1. The number of trials for that is 250 for A, University A. Now 7% for University B, so that's P2 is 0.07, and then N2 is also 250 for University B. All right, so it's important that you understand that the University A, I'm going to call that X1, and University B, I'm going to call that X2. Okay, so it's important that you understand that these are binomial variables, right? So it satisfies bins. B, they either choose business as a major or they don't. Independent, each student is independent from the next. The number of trials is the same, 250. The probability is the same for University A, and the probability is the same for University B separately. Okay, so there's two separate bins. So that means X1 and X2 are both binomial variables, okay? So X1, and then we're going to call this for X2, they're both binomial, okay? So what we're going to do is, it says we want the expected total number. So we're going to call that T for total, okay? So T is going to be X1 plus X2. That's going to be my total random variable. And we want the expected value of that. All right, so we're going to do the expected number. So the mu T, mu for the total, is the mu for X1 plus X2. Now, the mu, if you have two random variables here, you can actually do the mu of them separately and add them. Okay, so there you go. What's the expected value of a binomial random variable? Well, that's given in your AP formula sheet, and it's n times p. Okay, so that's the formula for that. So here we have n1 times p1 plus n2 times p2 because you have for 1 and for 2. And we can just plug in the numbers to get it, okay? All right, so let's just do that here. So mu t. So n1 times p1, we have n1, we said is 250, p1 is 0.19, and then n2 is 250, and then p2 is 0.07. Now if I combine those, I get about 65. So that means it eliminates these choices right here. It's either A or B. So this is what we have for the expected, now the number. Now we want the standard deviation out of the total number as well. So we're going to need to calculate that as well. Okay, so what's the standard deviation formula for a binomial? The standard deviation formula is square root of np times 1 minus p. Okay, now we're doing the standard deviation of the total, which is the standard deviation of x1 plus x2. But remember, they said that x1 and x2 are independent of each other. So that means we could use the formula for this. If they were not independent, we couldn't calculate this unless we introduced like some kind of correction factor or some kind of other factor. But that's beyond the scope of this. In order to do this, remember, it's a Pythagorean sum. So you have to do the Pythagorean sum, where it's square root of a squared plus b squared, the square root of, in this case, sigma squared x1 plus sigma squared x2. So you do the Pythagorean sum. All right, but now we know what sigma squared x is, and and sigma squared x2. So we're gonna plug that in. We know that. So let me just do it here. So sigma squared x1 is the square root of n1 p1 times 1 minus p1, right? But that's squared. And so because it's squared, it cancels out. So it leaves you with n1 p1 times 1 minus p1. Okay? So I'm going to do that here for the formula. And likewise, sigma squared x2 is going to be n2 p2 times 1 minus p1, right? So sigma squared x2 getting a lot of math there. So we got this, and that's what we have. So now we can just plug in the numbers and get an answer on the calculator, all right? So we got N1, P1, so 250 times 0.19 times 1 minus 0.19 plus, and I'm going to try to fit this in here. We got N2 250 times P2 0.07 times 1 minus 0.07. All right, there you go. Barely fit it in there. And do that calculation, you get about 7.40. All right, so then the answer has to be then A, cannot be B. All right, so this is a really good question to test your binomial, whether bins, and what the formula is for bins, as well as combining what we did with transformations in 6.2. Okay, they're combining a lot of things here. All right, so on number 32, the horse race is a popular carnival game in which multiple players shoot a stream of water at a target. Hitting the target moves their horse towards the finish line. The player whose horse crosses the finish line first is the winner. If 4 equally skilled players play the horse race game together, the probability that player A wins a given race is 0.25. In order to win a prize, player A must win at least 60% of races in a series of n races. If the possible choices of n are 5, 10, and 20, which value of n should player A choose in order to maximize their probability of winning a prize? All right, so this should be a binomial. So we have bins. B is for binary. So either they win or they don't. That each player is equally skilled, and they're independent of each other. So therefore, I is independent. And the number of trials is the same. We have depending on whether it's 5, 10, or 20 races that they do. But if we choose A, if we think it's A, then it's going to be 5 trials, and that's constant. And then S, the probability of success is the same as 0.25. Okay, so we want to see, and in order to win, you have to win at least 60% of the races. So we're going to calculate the probabilities for 5, 10, and 20 to see if they're the same, or if one is smaller than or if one is greater than the other one, because we want to maximize the probability, the chances that they win. Okay. All right. So let's go ahead and do n equals 5 first. In that case, we're going to use a binomial. Now, for at least 60%, 60% of 5 is 3. Okay? And then for B, 60% of 10 is 6. And then for C, 60% of 20 is 12. Okay? So we're just going to leave that aside for later. But we're going to need to win at least 3 games for n equals 5. Okay? So we want the probability that x is greater than or equal to 3. Okay, we want to win at least 3 games in order to win. Remember that this is greater than or equal to, so we want to use a binomial CDF function. However, it's greater than, so we want to make it less than or equal to. So what we're going to do is we're going to do the opposite. So the opposite of greater than or equal to 3 is less than 3. Okay, so we're going to do 1 minus the probability that it's less than 3, according to the complement rule. And then we want this to be less than or equal to, so I'm going to convert this into x is less than or equal to 2. Okay, if it's less than 3, that means it's less than or equal to 2. And then we can use the binomial CDF function. So 1 minus binomial CDF, n is equal to 5, p is equal to, the number of trials is 5, the probability of success is 0.25, and then their x value is 2 here, okay? So we're going to calculate that, and I'm just going to do it for all of these and see what we get. So let me just do this one. So this one's going to be probability that x is greater than or equal to, so we need to win at least 6 games for 60%, okay? So 1 minus the probability that x is less than 6, which is the same thing as x is less than or equal to 5, okay? So we're going to do 1 minus the binomial CDF of n equals 10, p equals 0.25, and x equals 25. Let's figure out what that is. All right, here we get p of x is greater than or equal to. So in order to win 60% of games, it has to be 12 games won. So 1 minus the probability, x is less than or equal to, oh, this should say x is less than, not less than or equal to. Sorry about that. Oh, no, that's fine. I'm sorry. That's correct. I was correct. And then this one's going to be x is less than or equal to 11. Okay, it's 1 less. All right, and then we get 1 minus binom CDF of n equal to 20, p equals 0.25, and x equal to 11. All right, and I showed you how to calculate these on the calculator, so I'm not going to do that. I'm going to defer. Not going to do that here. Actually, I am going to do it here because I think in the previous example I did the PDF function. So let's do it for the CDF function. Okay, so we're going to compare these. So we get 1 minus, and then we're going to do second vars. Go up here, or go down to the list, the bottom of the list. So that's CDF, not PDF. And then there. And then it's 5 trials, 0.25. X value is 2. See what that is. So we get 0.104. Okay, 0.104. Let's write that down. Okay, so we got 0.104, and then what we're going to do is we're going to repeat this. And we use the up arrow key to highlight this, enter, and then I'm just going to change these numbers. So this is going to be just to make it easier. So then this is going to be 5, right? And then this is going to be 10. So I'm going to hit second, insert, and then I'm going to do this as second, insert, 10. All right, so that should be good. Oops, I think I have 2 commas here. Let's delete that. Okay, and then we'll calculate that. Oh, look at that. It went down 0.0197. And then we'll do the next one. We'll copy that and change the numbers. So this is 11, and then I got to make sure I put parentheses there. And then this one here is 20. And look how small that is. That's almost 0. So that's move the decimal place to the left 4. 1, 2, 3, 4. So there's 0.3 zeros and then 9. So 3 zeros and then 9, 4. Okay, so we're going to write those numbers down. All right, so I've written the numbers so you can see that you have a greater chance of winning if you just have 5 games, which that makes sense because you only have to win 3 games as opposed to having to win a whole bunch of other games. All right, so the answer is A. All right, so it says of the Fortune 500 companies, the top 500 U.S. companies with the highest revenue, 10.6% are run by female CEOs. Suppose we choose a random sample of 30 companies from this list and count the number of companies in the sample that have female CEOs. Is the random variable of interest binomial with n equals 30 and p equals 0.106? Okay, so first off, does it satisfy bins, right? So does it satisfy bins? Well, B, either they're female or not. Each person is independent of each other. The number of trials is 30 companies. S, the probability of success, in this case getting a female CEO, is 10.6%. So yes, but now we want to see, remember that we're taking these people out, and so we're selecting without replacement, okay? So because we're taking the people and using them as part of our sample, we have to take them out of the population. So here we're sampling without replacement. So therefore it can't be, so because we're sampling without replacement, we need to satisfy a certain condition known as the 10% condition. If we satisfy the 10% condition, then we can say it's approximately binomial, okay? And we can approximate it. That's what we want to do. All right, the 10% condition states that the sample size has to be less than 10% of the population, okay? Less than 10% of the population. So here we have 30 people. Now, is that less than 10% of the population? Well, we have the top 500 U.S. companies, guys. There's a lot of people in those companies. If there's just 100 people in those companies, which is really small, that's already 50,000 or 50,000 people. So 30 is definitely, in this case, 30 is definitely way less than 10% of the population of all. This is not people, this companies, right? So in this case, there's 30 companies. So N is not the number of people, it's the number of companies. My bad. So we have 30 companies. Is that less than 10% of the population, which is 500? All right, well, let's see. What's 30 divided by 500? So 30 divided by 500 is 3 over 50, which is 6%, which is 0.06, which is 6% of the population. So that is definitely less than 10%. Okay, so we're good. We can say that the sample size is less than 10% of the population, and therefore we can approximate it with a binomial. All right, so that takes care of number 33. So it says let x be a geometric random variable with a probability of success given by p. So we're dealing with geometric now. Which of the following statements is true? Okay, so let's go ahead, since it's a geometric, let's write down what the formula is for geometric. So for geometric, the formula is for p of x is equal to, well, I guess I should say big X is equal to little x. Okay, so let me do that here real quick. For p of big X equal to little x, it's equal to, the formula is 1 minus p to the n minus x power times p. Or to the n minus 1. Sorry about that. Or, oops, not that, sorry. It's x minus 1. Okay, let me write that out. So x minus 1. X minus 1 power. So 1 minus p to the x minus 1 power, and then times p. So, all right, so let's see if that's true. So the p of x equal to 1 is 1 minus p to the 1 minus 1 power, right, times p. So 1 minus 1 power, that's 0. So that anything to the 0 power is 1, guys. So this is going to be 1 times p, or p. Okay? So the probability is simply just p. Now, if I do x equals 2, then it's 1 minus p to the 2 minus 1 power times p, which is just 1 minus p times p. Okay, so let's go ahead and do a little inequality here. So let's compare x equals 1 to x equals 2. So x equals 1, the probability is p. X equals 2, the probability is 1 minus p times p. And we want to know, is it greater than, is it equal to, is it less than, what is it? Well, first off, notice that these cancel, the p's can cancel. If this is an inequality or equation or something, that we can cancel it out on both sides, or divide it off. We can basically divide it off on both sides. Let's just do that. And if we do that, it becomes 1, question mark, because we don't know, and then 1 minus p. Which one, are these two equal? No, 1 is not equal to 1 minus p, right? So it can't be C, D, or E, because they're saying that it's equal. Or I'm sorry. It can't be E, I'm sorry, E, because it's saying that it's equal, right? So we have to see, is it less than, greater than? So 1 is always greater than 1 minus p. right? Unless P is 0, but you would never have a situation where P is 0, because otherwise how would we calculate a geometric probability? So P is always going to be a positive number. So that means 1 is always going to be greater than 1 minus P. So therefore, the probability of x minus 1, or x equals 1, is always going to be greater than the probability of x equals 2 for all values of P, right? Not including 0, because 0 is just a trivial value. All right, so here the answer is A. Okay. All right, so let's look at number 35. A fair six-sided die is rolled 4 times. Okay, so we have a six-sided die, and then 4 times. The first 3 rolls land on 1 or 2. What is the probability that the fourth roll also lands on a 1 or 2? This is a really simple question, but it looks complex if you're like overcomplicating it, right? So they're saying that the first 3 rolls are all 1 or 2. But then they're saying they're looking at the fourth roll. Does it really matter about the first 3 rolls? Well, no, because it should be independent, right? Each roll should be independent of the next. So it doesn't really matter what we have for the first 3 rolls, as far as, the fact that we got that 1 or 2. The probability of the fourth roll is just going to be simply whatever the probability is for that roll. So because they're independent, it's really simple. We just want the probability that it lands a 1 or 2. Well, there's 6 numbers on the die, so it's just going to be 2 out of 6 is 1/3. Okay, it's really as simple as that. Don't overcomplicate it and try to do like some crazy geometric formula stuff. Okay, just remember, understand the question. The rolls are independent, so really it doesn't really matter what the first 3 rolls do. The fourth roll is going to have its own independent probability that's going to do, and then it's 2 out of 6 or 1/3. All right, so let's look at number 36. Jared's friend stands 5 feet away and tosses gummy bears for Jared to catch in his mouth. Each toss has a 35% chance of success. Jared catching a gummy bear in his mouth, and the outcome of each toss is independent. Okay, is independent of the others. What is the probability that Jared's first successful catch occurs on the 3rd toss? Okay, so we can see that this is a geometric distribution, because if you look at the acronym FIBS, right, we have F is the first success, right? We have the first success occurring on the 3rd toss, right? So check, we have the first success, right? I, they're independent. B, it's binary, either he catches it or in his mouth or not. And then S, the probability to success is the same, 35%. So this is a geometric distribution. So we can just use the formula for the geometric. It says the first successful catch on the 3rd toss. So it's going to be the probability that X is equal to 3 on the 3rd toss. All right, and then so it's going to be, in this case, okay. So we got 1. Remember, the formula is 1 minus P raised to the X minus 1 power. So P is 0.35 raised to the X minus 1 power, so 3 minus 1, times P, which is 0.35. So we have here 0.65 raised to the 2nd power times 0.35, and that's it. And this formula, by the way, is given in the AP formula sheet, so you don't have to memorize it. So the answer is D. All right, so we're going to go ahead and continue. So we're going to do number 37. For each of the following situations, determine whether or not the given random variable has a binomial distribution and justify. Okay. All right, binomial, bins, right, guys? So bins, remember that. Remember that. So in a bookstore's top read shelf, 4 out of the 20 books are by the same author. All right, so 4 out of the 20 books. Suppose you select 3 books from the bookshelf at random. Okay. So let X be the number of selected books that are by this author. Okay. Right? So we just got to keep this in mind that if, since we're selecting the 3 books from the shelf at random, we're selecting these 3 books and we're not putting them back. And so it's selecting without replacement. So you want to be aware of that. Okay, so 3 out of 20 books is pretty significant, right? So that's about 15% around there, which is greater than the 10% condition. And the fact that you're selecting the 3 books without replacement, and it's going to change the probability of the next book being from the same author. So that fails the independence condition as well. Okay, so no, the trials are not independent because of selection without replacement. Okay, so now the part B, it says the internet at a certain cafe is not working 4% of the time. All right, so not working 4% of the time. Suppose you and your 4 friends each go to the cafe once at a random time over the span of a month, independently of one another. Let Y be the number of people in your friend group who go to the cafe and can access the internet, because we're talking about internet, it's not working. Okay. So if we satisfy bins, B, binary, either the internet works or it does not, right? I, each person is independent of one another. N, number of trials is the same. In this case, you and your 4 friends. So that means you have, so you have the same number of people that you're bringing with you. The number of trials is the same. And then S, the probability of success is the same. It's 4% of the time, right? It's always 4%. Okay, so yes. Each trial is binary. Can access internet or not. Okay, so they're binary. We mentioned independent. Number of trials is fixed. In this case, n equal to 5. And the probability of success is the same. P is equal to 0.96. Because it says can access the internet. So that means it's 1 minus 0.04, which is 0.96, okay? Is the same. All right, so that's it for that one. So let's skip to, we'll go to the next one. Number 38, in the game of Mac, if you roll 6 dice and earn 100 points for any die that lands on a 1. Okay, so you roll 6 dice, earn 100 points for any die that lands on a 1. And 50 points, okay, so, and 50 points for any die that lands on a 5. No points are earned for any other number. Let X be the number of dice that earn points from the initial roll of 6 dice. So they have to earn points. So that means that you have to have a 1 or a 5, right? So 1 or a 5. The dice that roll on a 1 or a 5, basically. Explain why X is binomial. Identify the number of trials, and so on and so forth. Okay, so each die well, here, let me just do this. There's either success or failure, right? There is success, 1 or 5, and failure. Not 1 or 5. Each die is independent. Okay, so each die lands independently of another. And the number of trials is fixed. I'm just going to put number of trials. Fixed. with n equaling to 6, we have 6 dice, and the probability of success is the same in this case. So in this case, the probability of success, you want to land a 1 or a 5, so that's 2 out of 6 options, which is 1/3. Okay? All right, so there you go. So it's binary, or it's a binomial. So now calculate the probability that exactly 4 out of the 6 dice earn you points. Okay, so the probability that x is equal to 4. Does this show your work? So we're going to show it. All right, so we want to, it says show your work, so that means we're going to be using the formula, but we can also use the calculator function, okay? All right, so the formula for the probability for binomial probability, let me write that here, is the probability that x is equal to n choose x times the probability of success raised to the n minus x power times 1 minus p to the x power. Okay, so that's what we got. Oops, sorry. It's I had to reverse these. Not it's x power here, n minus x power there, and then 1 minus p to the n minus x power. Okay, that's what it should look like. Okay. All right. So then let's use that formula. So we have here the number of trials is 6. So 6 choose 4 times the probability of success. It was 1/3. So times 1/3 raised to the 4th power. That's x. Times 1 minus 1/3 raised to the 6 minus 4 power. Okay, so there it is. Now I'm going to show you how to do this on the calculator. Remember that this is the same thing as this is the same thing as 6C4, the combination, right? So I'm going to do that on the calculator to show you. 1/3 to the 4th. 1 minus 1/3 is just 2/3, guys. So I'm just going to write it like that. 6 minus 4 is 2. So I'm going to show you how to do this, but you can also use the binomial PDF function. The number of trials is 6. The probability of success is 1/3, and x is 4. Okay, so we're going to show you both of these on the calculator just so you can refresh your memory on how to do that. Okay, right, here we go. So we're going to do the 6C4. Okay, so we're going to do parentheses 6, and then we're going to do the combination. So to do the combination, we're going to do math, probability, and then there's the NCR thing, so we're going to choose option 3. So 6C4, and then times 1/3, 1 divided by 3, raised to the 4th power, times 2/3 squared. Okay? And you got 0.08. So now let's show this with the probability, the binomial PDF. So second vars, go to binomial PDF, option A. And so that's 6 trials, 1/3, and then 4. All right, and you get the same exact value, 0.0823. All right, so 0.0823. All right, so let's look at the next question. Joseph Garrard III of Clemson University currently holds the record for the highest free throw percentage in men's college basketball, as reported by the association governing college athletics, NCAA. His free throw percentage is 95%, which represents the percent of free throws he successfully makes. Assume that he maintains his success rate and that his free throws are independent. Consider his 94 attempted free throws. Let x be the number of free throws that he makes. So how many of the 94 free throws would you expect him to make? Okay, so it satisfies Ben's. Either he makes it or not. Each throw is independent of the next. Probability of success is the same. The number of trials is N94. So we can calculate this, all right? Okay, so it says how many of the 94 free throws would you expect? So that's the expected value, right? The expected value of a binomial, which is in the formula sheet for AP, is n times p, okay? So in this case, it's going to be the expected is number of trials, 94, times the probability of success, which is 0.95. Okay, so if you do that, if you calculate that, you get 89.3. Let me double check that. Yeah, 89.3. Just wanted to double check. 89.3 free throws. Okay, so there's that one. So that's A. B, calculate the probability that x equals 89 and then interpret the result. Okay, so let's do that here. Probability x is equal to 89. Again, let's practice using the formula, but then we can use the binomial function. So we have 94 throws, choose 89, times the probability of success is 95%, 0.95, raised to the x power, 89, times 1 minus that. 1 minus that is 0.05, raised to the 94 minus 89 power, which is 5. Okay, if we have 89 successes, that means we have to have 5 failures if there's 94 throws total. And this is equal to the binomial PDF for n equal to 94, p equaling to 0.95, and x being equal to 89. All right, and then when we do that, we get about 0.1785. Okay, and we want to interpret that, of course, so because that's what they want. So I'm going to do B continued, okay? Just because of the sake of space. The probability that he makes exactly 89 of 94 free throws is 0.1785. Okay, so now let's do part C. Calculate the probability that he makes at least 92. Okay, so the probability of x is greater than or equal to 92. So in order to do this, we need to use the binomial CDF function, but we need to convert this to less than or equal to. So I'm going to do the opposite. The opposite of greater than or equal to 92 is less than 92. And less than 92 is the same thing as less than or equal to 91. So that way we can use the binomial CDF. Number of trials is 96 or 94, I'm sorry. The probability of success was 0.95, and x in this case is 91 for the function. All right, and if we do that, we get about, now we can use the binomial CDF function. That just makes things easier. So we should get about 0.1454. All right, so let's go ahead and go to the next one. So number 40. Leah is playing a carnival game in which she'll attempt to toss 5 softballs into a basket. The game attendant tells her that historically 27% of the softballs are tossed successfully into the basket, that the outcome of one toss does not affect the outcome of another toss, so independent. So far we got probability of success is the same, check, independent, and then she wants to attempt to toss 5 softballs, so the number of trials is the same. And it's binary. She makes it or she does not make it successfully. The game attendant will count the number of softballs she successfully does out of 5 attempts. Is the scenario binomial? That's what we were just doing here, right? Okay. We're just going to kind of explain it. So yes, each toss is either success or failure. Is either a success or failure. Makes it, doesn't make it. I'm just going to put it on the top there. Or failure. The outcomes are independent. Number of trials is fixed at n equals 5. And the probability of success is the same. P equals 0.27. Okay? All right, so B, find the probability that Leah tosses 3 softballs successfully. All right, so probability that X is equal to 3. Show your work. Okay, so we have 5 successes, choose 3, or five softballs that we threw, and then choose 3 successes, times the probability of success is 0.27 raised to the third power, times 1 minus that, which is 0.73, raised to the 5 minus 3 power, or 2. Again, we can use that, or we can use the binomial PDF. I'm showing you both just so you have both. So n equals 5, p equals 0.27, and x is equal to 3. All right, so if you calculate this, you get approximately 0.1049. All right, so now we're going to complete the table. So completing the table requires us to do the binomial formula a bunch of times. Okay, so we can either have 0 successes, 1, 2, 3, 4, or 5. Okay, I'm not going to show you all of them because it's going to take time to do all of them. Okay, guys, I'm just going to show you. We're just going to use the binomial PDF on the calculator. Okay, so I'm just going to show you 0. So for 0, we got binomial PDF, n equals 5, p equals 0.27, x equal to 0. And then do the same thing for x equals 1, 2, 3, 4, 5. We already did 3. So 3 was 0.1049. Okay? And then so if we do 0, we get 0.2073. Okay? If we do 1, we get 0.3834. And what I'm going to need to do is I'm running out of room, so I'm going to do it here. 0.3834. And then 2 is 0.2836. Okay, again, we're doing this on the binomial PDF function on the calculator. And then if I do x equals 4, this is going to become 0.0194. And then lastly, for 5, we can actually write it down here, 0.0014. Okay, so those are our values. Sorry, there's not much room to complete the table, but sorry about that. All right, so D. Leah will win a prize if she successfully tosses at least 4 softballs. Find the probability. So the probability that x is greater than or equal to 4. So we're going to do the opposite of that. 1 minus the probability that x is less than 4. Or the same thing as less than or equal to 3. Okay? So then this becomes 1 minus binomial CDF of n equal to 5 attempts. And then the probability of success is 0.27, and then x equal to 3. Okay? So yeah, so then we got that. So we get 0.0208 for the probability. Okay, so let's do number 41. In clinical trials, 22% of patients taking a new weight loss medication experience nausea after taking it. 20 patients take part in the study where they are given this new weight loss medication. Let n represent the number of patients who experience nausea. N follows a binomial distribution. Okay. Calculate and interpret the mean of the distribution of n. So the mean is the expected value. So the formula for binomial is n times p. Okay. So it's n times p. So that's the formula for binomial expected value. Okay. So it's going to be 20 patients, right? That was n equals to 20. And then the probability, that's p, that's 22%, so 0.22. That's going to be 4.4. And we want to interpret it, okay? So 4.4. So this means if the study repeated many, many times, with groups of 20 patients, the average number who experience nausea after the medication is about 4.4 patients. Okay. So now we're going to do the calculate and interpret the standard deviation. So standard deviation, the formula for standard deviation for binomial, which is in the formula sheet, is square root of n times p times 1 minus p. So we have square root of 20 times 0.22 times 1 minus 0.22. All right. I'm going to calculate that. We get about 1.85. 1.85 approximately. Okay, so if study repeated many, many times, with groups of 20 patients, then the 1.85, what that means is that the number of people who experience nausea would on average vary by that much, 1.85, from the mean of 4.4. Okay, so the average number who get nausea would typically vary from would typically vary by about 1.85 patients from the mean of the mean was 4.4. Okay. All right, so there you go. That's that. So find the probability that none of the patients in the study experienced nausea after taking the medication. All right, so the probability that n equals 0. Okay, and then show your work. Okay, so 20 patients choose 0 times the probability of success was 0.22 raised to the 0 patients times 1 minus that is 0.78 raised to the 20 patients. This is going to be about 0.0069. All right, and then of course we can use the binomial PDF. So let me just show you that. Binomial PDF, n equal to 20, p equals 0.22, and then x equaling to 0. Okay, you get the same answer. All right, find the probability that at least one patient in the study experienced nausea. Okay, so probability n is greater than or equal to 1. That's the same. That's the opposite of that is 1 minus the probability that n is less than 1, which is the same thing as 1 minus the probability that n is equal to 0. Okay, and we know that the n equals 0 is we just calculated it. 1 minus 0.0069, which is approximately 0.9931. All right. Okay. So 42. Determine if a binomial distribution can be used to model each of the following random variables and give a reason for your answer. Okay. Okay. All right. So rolling a fair six-sided die 8 times, counting the number of rolls that land on a 5. Okay. So that means the probability of success is 1/6. It's independent, right? Because it's a fair six-sided die, so it's going to be independent every time. And then the number of trials is the same, 8, right? N is equal to 8. Okay, so yes. So this is yes. Each trial has success, which is a 5, or failure, not a 5. Rolls are independent. Probably the number of trials is 8, And then probability is 1/6. Okay? This should say 8. All right, randomly selected 5 cards from a standard 52 card deck without replacement and counting the number of cards that are hearts. Okay? All right, so the fact that we're not replacing them, meaning it's not meeting the independence condition. So because it's not meeting the independence condition, we have to test to see if it satisfies the 10% criteria. Okay. So let's see if that's the case. So does it meet the 10% condition? Let's find out. So there's 5 cards selected. So 5. And then there's a total of 52 cards, right? And so we have to do 10% of 52. So 10%, 0.10 times 52 is 5.2. So 5 is less than 5.2. Check. So that means 5 is less than 10% of the deck. So this is okay. We can use the binomial approximation for this, okay? We can approximate it. So we're going to say yes, okay? Each trial has success, meaning hearts, or failure, not hearts. Okay? And then, and even though there is selection without replacement, the 10% condition is passed. With 5 being less than 5.2. Okay? So we're good. The number of trials, and we know that n is equal to 52, right? The number of trials, or 5, I'm sorry. And probability of success. Now, what's the probability of getting hearts, guys? The probability of getting hearts, in this case, is, well, there's four suits: hearts, diamonds, and then you have spades, clubs, right? So it's 1 out of 4. Okay, so probability is the same. All right, so yes. Part C, writing the numbers 1 through 20 on 20 separate slips of paper, putting them in a hat. Okay, so 20, putting them in a hat and randomly selecting 5 of them. Then counting the number of selected slips out of 5 with an even number written on them. Okay, so binary, yes, either they have an even number or not. Let's see the 10% condition. 10% question mark? So 10% in this case, so 10% of 20 slips is 2, sorry. But we selected 5 slips, right? We selected 5 of them. Yeah, we selected 5, and 5 is not less than 2. So it fails the independence condition. So no, it fails the 10% condition. Independence condition is not met since selected without replacement. And 5 is not less than 10% of the population. Five is not less than. I was trying to cancel this out. All right. 5 is not less than 2. All right. All right. So there you go. So that's that. All right. So let's go to the next one. Number 43. According to a study from the Pew Research Center, 76% of Americans traveled outside of the U.S. at least once. A random sample of 150 Americans was selected. Consider the number of Americans in the samples who had traveled outside at least once. Define the variable interest and describe how it is distributed. Okay, so we're interested in the number of Americans in the sample. Okay, so who have traveled out. So we're going to say X is the number of people out of the 150, right? Who traveled outside of U.S. at least once. Okay, and we want to say, is it distributed? Well, does it satisfy bins? So either they have or they have not traveled outside at least once. Each person is independent. Number of trials, 150 is the same. Probability of success is the same, 76%. Okay, so X, we're going to say X is a binomial random variable. Okay, all right, so each trial has success or failure. Each person independent from the next. Number of trials, n is 150, and then probability of success is 0.76. Okay, there you go. All right, part B. Use a binomial distribution to calculate the probability that at most 110 people in the sample have traveled outside the U.S. Oh, also we have to. I forgot. Also, we have to calculate the 10% condition for our part A. So I forgot to do that. Each person independent from the next, and then I'm going to put here that 150. We have 150 people. 150 is less. 150 is less than 10% of all Americans. Okay, I forgot to put that. So the 10% condition is met, so we can use it in the binomial distribution. So use a binomial distribution to calculate the probability that at most 110 people in the sample have traveled outside of the U.S. At most. Okay, so all right. So we're going to calculate that. Probability at most is less than or equal to 110. So we can use the binomial CDF function right away because it's less than or equal to. Number of trials is 150. Probability of success is 0.76, and X is 110. All right, calculate that. And then if we calculate that, we get, okay, so that's going to be about 0.2488. Now, justify why the variable defined in part A can be approximated by a normal distribution. Okay, so this part we haven't done yet so far in this study. So justify why it can be approximated by a normal distribution. All right, so the reason why we can do a normal distribution is because it satisfies the large counts condition. Okay, so the large counts condition. The large counts condition says that NP is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So in this case, it does satisfy because we have 150 Americans times the probability of success is 0.76, and that is greater than that is if we calculate that, that's 114, which is greater than or equal to 10. So check. And then the other condition, 150 times 1 minus 0.76, that's equal to 36, which is greater than or equal to 10. Okay, so we can approximate it by a normal distribution. What is the mean and standard deviation? Let's do that here. So the mean is n times p. Okay, we're going to say x is the number of Americans, so mu x. Okay, and then n times p, that's going to be, we just calculated that. That's 150 times 0.76, and that's 114. This NP is for the binomial formula, okay? And then the standard deviation is square root of NP times 1 minus P. So square root of 150 times 0.76 times 1 minus 0.76. And if you calculate that, that's approximately 5.231. All right. So use a normal distribution to estimate the probability that at most 110 people have traveled outside of the U.S. Okay, so again, we have a normal distribution where the center is 114, and it goes by 5.23s, okay, to the right and to the left. I'm not going to write all those numbers, but we want this to be at most 110, so it's going to be 110 people. We want to shade to the left, okay, so we want it to be at less than or equal to. So the probability that x is less than or equal to 110. So we're going to use the normal CDF function. And remember, you need the lower value, the lower limit. Let's actually, I'm going to lasso this and put this down here because I'm writing kind of big. All right, let's do that. Normal CDF, the lower limit is in negative infinity, right? Because it's a big negative number, so negative 10,000. The upper is 110, right? And then our mean is 114, and our standard deviation was 5.231. So we're going to calculate that. We're going to get the answer right away. So it's about 0.222 approximately. All right, so let's go ahead and look at the next question. All right, the Environmental Working Group has a database with nutritional information of more than 84,000 foods. 27 of these foods contain trans fats. OMU wants to investigate how many items contain trans fats. She selects a random sample of 200 foods. Let F be the number of foods in a random sample of 200 that contain trans fat. Assume that the grocery store has the same percent of foods with trans fat as the database. All right. Explain why F can be modeled by a binomial distribution, even though the foods are selected without replacement. Well, the 10% condition, right? 10% condition. It says, so if we were to do the 10% condition, we would have we have 200 foods, right? Is less than 10% of all foods at a large grocery store. 200 foods is not that many, considering like all the foods at a large grocery store. Okay, so we can assume that this is true. Okay, so therefore it can be modeled by a binomial distribution. B, how many foods in a sample of size 200 would you expect to contain trans fats? So we have to calculate the mean. Remember, the mean is n times p, which in this case we have 200 foods times the probability was 27%. That's my p, okay? That would be 54 foods, okay? So that's B. In repeated samples of size 200, by how much would you expect the number of foods to typically vary from the expected number? That's a standard deviation, guys, that they're asking. So sigma F equals square root of NP times 1 minus P. So we have 200 times 0.27 times 1 minus 0.27. So that's going to be approximately, if we calculate that, 6.28 foods. Okay, so that's for part C. Okay. This is for that. So D, describe the shape of the distribution of F. Give a reason for your answer. Now we know that it can be modeled by a binomial. Can it be modeled by a normal distribution? Well, let's look at the large counts condition. N times P has to be greater than 10 or equal to 10. The N is 200. So 200 times the probability is 0.27. We've calculated that already. That was 54, which is greater than or equal to 10. So check. We also have to test 200 times 1 minus 0.27. And in that case, that's going to be 146, which is greater than or equal to 10. So therefore, has to be normally distributed, approximately. Okay, so we can say it's approximately normal. Okay. All right. So now let's look at E. Suppose Omu found 74 food items in her sample to contain trans fat. If the true proportion of foods containing trans fat is actually 0.27, what's the probability of getting Omu's result or greater? So result or greater. So 74 or greater. And use a normal approximation. Okay, so we don't want to use binomial. We want to use a normal approximation. All right, so remember that we have a normal distribution where the center of it is the mean, which is 54. If you recall, that was 54. And the standard deviation, it goes by sixes, 6.28 on either side. And we want 74 or greater, right? So 74 or greater. So we're going to use a normal CDF. Probability that x is greater than or equal to 74 is normal CDF. The lower is 74. The upper is infinity, or a really big number, so 10,000. The mu is 54, and then the sigma is, we said it was 6.28. So if we calculate that for Omu, we get about 0.0007. Okay, so that's for part E. Again, not a lot of room, but and then does Omu have convincing statistical evidence that the true proportion of foods with trans fat is actually higher than 0.27? Well, 0.0007 is actually less than 5%. Remember the cutoff was 5%. Is less than 0.05. Okay, so that means there is convincing evidence. Okay, so yes, there is convincing evidence that the true proportion of foods with trans fat is higher than 0.27. Okay? All right, so there you go. Number 45. Determine if each of the variables described below is a geometric random variable. The study suggests approximately 10% of people are left-handed. While waiting in line, Cal asks each person in front of him whether they're left-handed or right-handed. Let X be the number of people he must ask until he finds the first who is left-handed. So remember fibs. Remember fibs. The first success, yes, until he finds the first person. Check. Independent. Each person is independent from the next. Yes. B. B stands for binary. So binary. They're either left-handed or they're not. S. The probability of success is the same. 10%. Okay. So good. So yes. And then let's define it. So each trial has success or failure. They're not left-handed. We can assume independence outcomes for each person. Handedness is independent from one person to the next. So that's I. B, we did the binary first. So the number of people, the random variable. Okay. We are looking for the first success. That's the F in fibs. And the number of trials is, or the probability of success is the same. And P is 0.10. Okay? All right, so a large study found that 69% of adults prefer drinkable desserts over edible ones. So 69%. Assuming that this result is true, exactly 8 people and asks each of them if they prefer. So he talks to 8 people and asks each of them if they prefer drinkable or edible desserts. Let y equals the number of people out of 8 who prefer drinkable desserts. Okay, so this fails. By the way, this fails the F, right, in fibs because you're not looking for the first success. So no, since y is not the number of people asked until you get the first success or first person who prefers drinkable desserts. Okay, so it fails the F. You're not looking for the first person who prefers drinkable desserts. All right, number 46. According to a survey from the Pew Research Center, 33% of workers respond to work-related emails outside of work hours often. Assume this is true for Reagan's list of Facebook friends. Reagan starts asking randomly selected people from her list. Assume the responses are independent. Reagan is interested in knowing how many people she'll have to ask until she finds the first one who says often. Okay, so this is F in fibs, right? Define the random variable interest and state how it's randomly distributed. Okay, so all right, so let's say x equals the number of people asked until she finds someone who reported often. Okay, so this is a x is a geometric random variable with p equaling to, now the p is 33%, right? So p is 0.33. Now, what is the probability that Reagan must ask 5 people until she finds someone who responds often? So the probability that x is equal to 5. Remember the formula is 1 minus p to the x minus 1 power times p. So it's 1 minus 0.33 to the 5 minus 1 power, or 4. I'm just going to write 5 minus 1 times 0.33, which is the same thing as 0.67 to the 4th times 0.33. And that's about, this is the same thing as the Geomet PDF function. I'll show you how to do that. Geomet PDF function. Okay, and you need the probability of success, so P is equal to 0.33, and then X is equal to 5. Okay, so you calculate that. Let me show you the Geomet function on the calculator. Okay, so we have, we're going to hit second vars, and we're going to go to the very bottom of the list, so we get to Geomet PDF. We want PDF, guys, because we're dealing with only one value of X, not less than or equal to. All right, we got P is 0.33 down, and then we got 5 for the X. Okay, so there you go. 0.0665 around there. Okay, so around there, 0.066. I'm just going to round it to that. Okay. Now, what's the probability that Reagan must ask less than 3 people until she finds someone? So less than 3. So the probability is less than 3, which that's the same thing as 1 minus or that's the same thing as the probability. Oops, sorry. This is the same thing as the probability that x is less than or equal to 2. Okay. If it's less than 3, then it's less than or equal to 2. And then we can use the GeoMet CDF function. CDF is for less than or equal to, guys. So you got p equals 0.33, and x is equal to, now we're going to use 2. Okay, we can show you that. All right, here we go. So we're going to second, and then vars, and then we're going to go down. We're going to go to GeoMet CDF, the very last one. 0.33, and the x value is 2. Okay, so we got 0.5511. All right, and now what is the probability that Reagan must ask 3 or more people? Okay, so probably x is greater than or equal to 3. Now, the opposite of greater than or equal to 3 is less than 3. And we just calculated that. We calculated that in part C. So it's 1 minus 0.5511, which is 0.4489. All right, now how many people should Reagan expect to ask before she finds someone? Expected value. So the formula for the expected value for a geometric distribution is 1 out over p, okay? So that's all we have to do. So mu of x is equal to 1 over p, which is 1 over, and then p is 0.33. Okay, so this is approximately 3 people. When you calculate it, you get about 3.03, which is about 3 people. And then the formula for geometric distribution for standard deviation is square root of 1 minus p divided by p. Okay, so we have sigma x is square root of 1 minus 0.33 divided by 0.33. So that's approximately 2.48 people. All right, wrapping this up here. So last one, 47. Renaya is the manager at a local restaurant and has noticed that her employees sometimes forget to include silverware in the to-go orders. Based on the customer feedback, Renaya estimates that this occurs about 18% of the time where they forget. Okay, assuming it occurs independently. What's the probability that the first, so that's the F in fibs, okay? So F, independent, binary, success, 18%. But what's the probability that the first 5 all include silverware, but the 6th order does not? So that means that this is a geometric. So we have x equal to 6 because the 6th order does not, right? So the 6th order, that's the first success. Success in this case is defined as forgot silverware. Okay, so the first success is the 6th one. All right, so it's 1 minus the probability of success, which is 0.18, times raised to the x minus 1 power, times the probability of success. Okay, we can also use the GeoMet PDF function and say p is 0.18 and x is 6. Either one of those is correct. And then if we do that, we get 0.0667 approximately. All right. So that's for, hold on a second. Yeah. Okay. Now, what is the probability that the first to-go order on a particular day that doesn't include silverware is the 21st order or later? Okay, so 21st or later. So that means it's greater than or equal to. Okay, so probably the x is greater than or equal to 21. We're going to convert that to less than or equal to. So the opposite of greater than or equal to is less than 21. And less than 21 is the same thing as saying less than or equal to 20. Now we can use the GeoMet CDF function because it includes less than or equal to. P is 0.18, and X is 20. Okay, so we calculate that, and we get 0.019. All right, if the first 20 to-go orders on that day all include silverware, is it reasonable to believe that employees forget to include silverware less than 18% of the time? Okay, well, first off, we the probability that we get 21 or more, right, is 0.019, right? So the probability that the first 20 orders have silverware is 0.019, which is less than the 5%. And so that means that there's enough evidence, there is convincing evidence to believe that the probability that they don't include silverware is less than 18.18. Okay? There's enough evidence for that based on the probability we calculated. All right, we should be looking at the last problem here. So that's okay. So there you go. So Ephraim made a Spotify playlist of 40 songs, some of them which are by his favorite band, Mumford and Sons. When he gets ready in the morning, Ephraim plays this playlist on a special shuffle setting that allows for repeats. Let X be the number of songs he listens to until he hears one by Mumford and Sons. A portion of the probability distribution of X is shown. Complete the probability distribution for X equals 2, X equals 3, X equals 4, and X equals 5. Okay. All right. So it says let X be the number of songs he listens to until he hears one by Mumford and Sons, and he has a playlist of 40 songs. Okay. Okay. And then notice that it allows for repeats, so that means the probability of success is going to be the same. All right. Now we don't know how many of we don't know direct right now without digging in how many are by his favorite band. So we don't know what the P is, but we can calculate what the P is. So let's calculate that because they give us for X equals 1. So the probability for X equals 1 is, remember the formula is 1 minus P to the X minus 1 power, so 1 minus 1 times P. 1 minus P to the 0 power is just 1, so this is just going to be equal to P. Now they told us that X equals 1, the probability was 0.40, right? See that there? So we now know that P is 0.40 based on that. So now we can go ahead and calculate the other ones. So X equals 2, 1 minus 0.40 raised to the 2 minus 1 power for X equals 2 times 0.40. And then we can do X equals 3, 1 minus 0.40 to the 3 minus 1 power times 0.40. And then X equals 4, so on and so forth. All right. And so then we can actually calculate that. We'll see what we get. So we can calculate that. I'll tell you what I get. All right, and this is what I get when I do this on the calculator. So now we can go ahead and graph it. So for X equals 2, we got 0.24. For X equals 3, we got 0.144. For X equals 4, we get 0.08, so almost 0.09, close to 0.10. And then for 5, we get 0.05, so right around here. There you go. And notice that it's skewed to the right, just like a geometric distribution always is. All right, that's going to do it for the video, guys. Hope you found this useful and informative. And as usual, I'll see you in the next one.